All right, let's solve a chemical mystery, shall we? Today we're diving into something called acid-base titration.
So, let me ask you something. How do you measure something you literally can't see? I mean, think about it. You've got this clear, colorless liquid. You can't just look at it and know how strong it is. We need a really clever way to uncover its secrets.
So, think of this as our laboratory crime scene. Our whole mission, our entire investigation, is to figure out the secret that's hiding inside this little flask.
All right, so let's set the stage for our chemical mystery. We're calling this one the case of the unknown concentration. Okay, so here's the mission. Plain and simple. We have this hydrochloric acid solution. That's our suspect. The problem? We have no idea how strong it is. Our job is to find its exact concentration, what chemists call its molarity.
Now, you can't solve a case without the right tools, right? So let's take a look inside our detective's toolkit.
Okay, every detective has their kit, and here's ours. First up, the suspect. That's our unknown HCl solution. Then we have the standard. This is our sodium hydroxide, and we know exactly how strong this one is. Our informant? That's a chemical called phenolphthalein. It's going to tell us when the case is cracked. The whole thing goes down in the interrogation room, which is just our Erlenmeyer flask. And to measure everything super precisely, we've got our polygraph, a 50-milliliter burette.
Let's talk a little more about our informant, phenolphthalein. Honestly, this stuff is our secret weapon. It's a special dye that's totally clear when it's in an acid. But, and this is the magic part, the exact moment our mystery is solved, it flashes us a signal by turning pink. It is absolutely key to this whole investigation.
Okay, so before we jump into the lab work, we got to understand the rules of the game. How does this all actually work? It all comes down to a really fundamental idea in chemistry.
And that idea is molarity. You'll see it written as a capital M. It's just a way of talking about concentration. Basically, it tells you how much stuff, how many moles of a substance is packed into 1 liter of a solution. And that is the exact number we're trying to hunt down for our mystery acid.
So here's the central plot of our story. You've got acids, like our HCl, and you've got bases, like our NaOH. They are total chemical opposites. When they meet, they neutralize each other. It's kind of like a chemical tug-of-war. What we're looking for is that perfect moment when it's a dead tie. And this is the master equation. It looks simple, but this little formula is the key to cracking the whole case. It's just Ma times Va equals Mb times Vb. Basically, the molarity of the acid times its volume equals the molarity of the base times its volume. The beauty is, once we figure out 3 of those numbers, we can just do some simple math to find the 4th one, our unknown concentration.
Okay, enough theory. It's time to get our hands dirty, right? Let's walk through the actual investigation step by step. This is what I call the art of the drop.
So, here's the procedure. It's all about being methodical. First, you write down the starting volume of the base in your burette. Super important. Step 2, you add a very precise amount of your mystery acid to the flask along with a couple drops of our informant, the indicator. Then, the careful part. You slowly add the base from the burette, drop by drop by drop, swirling the flask the whole time. And finally, you stop. The very second that solution turns pink and stays pink, you stop and write down that final volume.
And listen, I really want to hammer this point home. Titration is not to be rushed. You have to take this slow. Seriously, every single drop matters. If you add just 1 drop too many, poof, your data is ruined. This whole thing is a game of patience and precision.
And this is the moment we've been waiting for, the big aha moment. It's amazing to see. 1 single drop, literally 1 drop, will change the whole solution from perfectly clear to this faint, permanent pink color. That's it. That's our signal. That's the end point.
Okay, we've done the work, we've seen the color change, our evidence is collected. Now it's time to head back to the office, you could say, and crack the code.
Just like any good detective, we need to keep meticulous notes. This data sheet is where it all comes together. We log our starting volumes, our final volumes, everything. And when I say precision is everything, I mean it.
So, let's look at a sample run. Let's say it took exactly 22.50 milliliters of our base to get that pink color. That number right there is the key piece of evidence.
That's the clue that's going to solve the entire mystery.
Okay, now for the fun part. We take that number, 22.50 milliliters, and we plug it into our master equation. We already know the other pieces of the puzzle, the concentration of our base, the volume of our acid, so we just do a little bit of algebra and boom, we crack the code. The concentration of our unknown acid is revealed to be 0.09 molar. Case closed.
But wait, a good detective or a good scientist never trusts just one piece of evidence, right? You gotta be sure. That's why we do this whole thing multiple times. And look at these results from a few different trials. They are all super, super close. That's what gives us confidence that our answer isn't just a fluke, it's reliable.
So, okay, we solved the mystery in our flask. But, so what? Why does any of this matter in the real world? Well, it turns out this is way more than just a cool lab experiment.
The truth is, this technique is used absolutely everywhere. You want to make sure the orange juice you're drinking has the right amount of citric acid? That's titration. Checking the purity of medicines? Titration. Even monitoring the health of rivers and lakes by checking their acidity. It's a fundamental tool for all kinds of real-world investigations.
Think about what we just did. We started with a liquid that looked just like water. And with a little bit of logic, a few clever tools, and a splash of color, we uncovered its hidden secret. It's just a perfect example of what chemistry lets us do. So I'll just leave you with this thought. Now that we've seen how to measure the invisible, what other secrets are hiding out there, right in plain sight, just waiting for us to uncover them?